Hi again, everyone. All right, so I'm going to go over section 4.5 with you a little bit, which is the summary of curve sketching. We're going to take a look at what guidelines you should follow when you're sketching a curve, or the graph of what a curve will look like. And then we're also going to do one example. These do take a while, so I'm only going to show you one example on this video, and then you'll have a few more to practice so that you get the idea of how to follow these guidelines. You should have a printed paper that was attached to the email where it has a listing of the guidelines on it. You can copy into that as I go through the notes here so that you have a page with the guidelines on them that you can follow for your examples. So I'm going to start by taking a look at our guidelines for curve sketching. Okay, so for the first part, okay, what we're going to do is find the domain. So we've talked about finding the domain before, so you guys pretty much know what to do there. I'm not going to go over that one, but the domain is going to be very helpful for parts later in the curve sketching. So that's the first thing that you want to do. Okay, next step would be to find the x and y intercepts. For this, you just want to set x or y equal to 0, depending on which one you want to find. So for x, set y equal to 0. To find the y-intercept, you're going to set x equal to 0. Okay. Third, we're going to want to look for the symmetry in the graph. Okay, so I'll go into this one a little bit more. Even functions, when we plug in negative x into the function, we get the original function that comes back out. So we know that this graph would have symmetry in the y-axis. If f is an odd function, if we plug in that negative x again, we get the opposite function. And we also can conclude that it's symmetric about the origin. And finally, for functions that are periodic, what we want to do is work with just one interval equal to the length of the period. So for example, for a function y equals sine x, we would consider just one period of the function, which goes from 0 to 2 pi. Then we would translate to sketch the rest of the graph. Okay, so that's symmetry. Again, pause the video if you need to take a minute to copy this down, but I'm going to continue on. Next thing we're going to take a look at is the asymptotes, both horizontal and vertical asymptotes. Okay, for horizontal, we know to use the limits as x approaches positive and negative infinity. And for vertical asymptotes, this is where having the domain is going to be handy. You're going to choose values where either you have endpoints for your domain or restrictions on your domain, and then check those values to see as the limit approaches that number. So here we're saying as x approaches a, what is the limit approaching from both sides? Okay, you'll see those show up in an example, but we've done this before. Also, there are things called slant asymptotes. Okay, so if the graph approaches a slanted line or some kind of a diagonal line in the coordinates, but we're not going to cover those in this section. Okay, part E we're at. For this part, we're going to take a look at the intervals of increase or decrease. So this is what we've been doing here, talking about the first derivative. So we're using the increasing-decreasing test. If f prime of x is greater than 0, we know that it's increasing on that interval. And if it's less than 0, then that's where it's decreasing. So we're going to determine what those intervals are. Okay, then we go to part F, which is actually related to part E. We're going to figure out what our critical numbers are and use that to find the local extrema. So critical numbers, remember, are where the derivative either equals 0 or doesn't exist. And the local extrema, we look for a sign change from max to min or min to max. So if it goes from a maximum, it's a local max if it goes from positive to negative, sign change, and it's a local min if the derivative goes from negative to positive. Okay, part G, getting towards the end now. We're going to test the concavity and points of inflection. So we're going to use the second derivative for this one in the concavity test. If the curve, the curve is concave up where the second derivative is greater than 0, and it's concave down when the second derivative is less than 0. Our points of inflection occur when the derivative changes sign, meaning the concavity changes. So we're going to find spots where the second derivative equals 0 or where it does not exist. Okay, so once we've done those parts, we are on part H here at the end. And this is where we're finally going to be able to sketch the curve using all of the information we collected in parts A through G. So I'm going to show you, oh, sorry, this is the paper that you're going to use. Each time I would write out the steps for the guidelines and put in the information. So I'm going to follow along this pattern for the next example we do here. You'll see that they show up below. And we're going to sketch this curve f of x equals 2x squared over x squared minus 1. So I'm going to start by determining the domain of this function. So I can see that I have a denominator, x squared minus 1. So I know there's going to be a restriction on the domain because x squared minus 1 can't equal 0, which means x squared cannot equal 1. And that's going to lead me to x cannot equal positive or negative 1. So my domain is going to contain x values from negative infinity to negative 1 to positive 1, and 1 to infinity. All right, that's going to help us later with the vertical asymptote. So I'm going to move on to part B, where I'm looking for the intercepts. So for this one, when x equals 0, I check out the function, I can see that I'm going to get y equals 0. So these actually have the same intercept. Both intercepts are at 0. So I really just know one point now. These intercepts are going to occur, or the one intercept is going to occur at the origin, 0, 0. Okay, so that is one thing I can actually go right back up to my graph. Give me my first point so I can plot that on there and use that later. Okay, so part C, determine if we have symmetry. So I'm going to take my function and I'm going to plug in the opposite of x. So that would be 2 times negative x squared over negative x squared minus 1. And I get 2x squared over x squared minus 1, which is my original function. This tells me that the function is even. And this means that it has symmetry in the y-axis, or symmetry about the y-axis. Okay, so that's going to be something that I can use to check later, make sure that I have a graph that has the symmetry about the y-axis. Okay, we're at part D. We're going to look for the horizontal and vertical asymptotes. All right, for this one I'm going to start with the horizontal. So I know I'm going to do the limit as x approaches positive and negative infinity. Okay, for this one we'll see that this is actually going to turn out the same, so I can just consider both at once. Since the degree of the numerator and the degree of the denominator are the same, I can use the ratio of the leading coefficients. So this limit is going to be 2. Which tells me that y equals 2 is a horizontal asymptote. Okay, and next I'm going to do the vertical asymptote. So this is where the domain comes in. I know that my domain was restricted so that 1 and negative 1 are not part of it, which means I'm going to check at those values to see if maybe these are vertical asymptotes. Okay, so I'm going to use a different color so that we can see that one. Kind of squeeze this in over to the right here. So the limit as x approaches 1 from the right. For now, I'm just going to write f of x for the function. Okay, so when I check that out as I'm approaching 1, I can see that I'm going to approach positive infinity for my function. Okay, when I look at x approaching 1 from the left, I'm going to approach negative infinity. So right there, I know I have one vertical asymptote, but let me check out the other value. So the limit as x approaches negative 1 from the right. This time, as I approach negative 1, I'm going to approach negative infinity. Okay, get a little bit more room here. And the limit as I approach negative 1 from the left, I'm going to approach positive infinity. So I just found 2 vertical asymptotes, x equals 1 and x equals negative 1 are both vertical asymptotes for my function. Okay, so again, you can sketch along the way. You don't have to wait until you've done all up through part G before you start sketching. So horizontal asymptotes are a great, both sets of asymptotes are a great place to start. So I'm actually going to go right up to my graph now and sketch both of these sets of asymptotes. Okay, and I know I have horizontal at y equals 2. So I'm going to sketch that one here. And then I have my vertical at x equals 1 and negative 1. All right, so I've got those three on there now. Okay, back to work here. We're going to go on to the next part. So part E is where we're looking for the intervals where we have an increasing or decreasing function. So I need the derivative. Okay, so I'm going to do the derivative for this one on the next slide, just so I have a little bit more room. So f prime of x, I'm going to need to use the quotient rule here. I do the bottom function, x squared minus 1, times the derivative of the top, 4x, minus the top function, 2x squared, times the derivative of the bottom function, 2x, all over that bottom function squared. Okay, I can do a little bit of simplifying up here in the numerator. Okay, if I multiply out the top, I get 4x squared minus 4x minus 4x cubed. Sorry, I messed up earlier. It's 4x cubed minus 4x cubed. Okay, denominator hasn't changed. But I can cancel out the 4x cubed with the negative 4x cubed. So my derivative is negative 4x over x squared minus 1 squared. Okay, and to determine where it's increasing or decreasing, I have to know what intervals to look at. So this is going to equal 0 when the numerator equals 0. So that's going to happen when x equals 0. So I'm going to take a look at the intervals from negative infinity to 0 and from 0 to positive infinity. Okay, well, looking at my derivative that I have right here, when I consider plugging in negative numbers, I know that the numerator is going to end up positive, and the denominator, since it's squared, is always going to be positive. So when f prime of x, when x is less than 0, when x is a negative number, f prime of x is going to produce positive over a positive, so it's going to be greater than 0. Okay, the only exception is at positive 1. Okay, so we're saying x is not going to equal 1 because it doesn't actually exist there. Okay, if I look at it in the other way, x is now greater than 0, positive numbers. I look back at my derivative, so the numerator is going to be a negative value. The denominator is always positive, so that produces a negative, which means the derivative is less than 0. And for this one, x cannot equal positive 1. Sorry, for the other one, it was negative 1. Okay. All right, so now I know where my intervals are for increasing and decreasing. Since f prime of x is greater than 0 when x is a negative number, that's where it's increasing. So I'm going to go back to my last page here, and I'm going to write my information. So f of x is increasing on the interval from negative infinity to negative 1 and then negative 1 to 0. So from negative infinity to 0, but not including negative 1, since it doesn't exist there. And f of x is decreasing on the interval from 0 to 1 and from 1 to infinity. So all positives except 1. Okay, I'm going to keep going. Next one, we're looking for local maxes or mins. For this one, we just need to determine our critical numbers first and then figure out if there's a sign change. So critical numbers are where the first derivative equals 0 or does not exist. So let me go back to my first derivative here. I already figured out that it equals 0 when x equals 0. And if I look for where it doesn't exist in the denominator, since all of those numbers are positive, I'm never going to end up with, oh no. Sorry. So when I look at the denominator, I know that they're always going to be positive or 0, but I've already determined that at positive and negative 1, I know that I have vertical asymptotes. So I can't have a max or a min there anyway. So even though the derivative doesn't exist at those values, I'm not going to consider those. So the only critical number that I have to consider is x equals 0. Okay, so x equals 0 is the critical number here. And when I look at that value, I have to check what's happening to the function. So I'm going to go back up to e, because I'm going to see where it's increasing and decreasing. So f prime of x is going from positive to negative. So it changes from positive to negative at x equals 0. So this means that f of 0 equals 0 is a local max, since it's going from positive to negative. All right. Last part before we can start completing our graph. So to determine the concavity, I'm going to need to use this second derivative. All right, I'm going to go to another screen here so I can calculate my second derivative. So f double prime of x. Use my first derivative function, so derivative of that, bottom, quotient rule again, bottom times the derivative of the top, minus the top function times the derivative of the bottom. Here I actually need the chain rule to get that derivative. And then all of that's going to be over that bottom function squared, which means it's now to the 4th power. Okay, so there is some simplifying we can do with this function. All right, I'm just going to skip over this a little bit. I can cancel out one of the x squared minus 1 terms, since it's in all of them. Change that to a cubed. Okay, and then I'm going to be able to cancel out a few more. So I'm just going to show you how this simplifies. You can actually go through these steps on your own. But I end up with 12x squared plus 4 over x squared minus 1 cubed. Okay, so that's my second derivative. So I need to figure out what intervals to check here for concavity. So I'm going to look at where this function equals 0 or doesn't exist, but I'm going to start with 0. So in the numerator, I know that I actually always am going to end up with a positive value. So there are not going to be any places where the function equals 0. Okay, so there are none there to consider. That means that I'm really just going to have to figure out what the signs are for this function to determine when it's concave up and concave down. So I'm going to use the denominator here, because I know, again, the numerator, always positive. So because of that, the denominator is really going to tell me when the whole fraction, the whole function here, is positive or negative. All right, so let me put this down below. I know that x squared minus 1 cubed, the denominator, is going to be greater than 0 when x squared minus 1 is greater than 0. Okay, and then that means x squared has to be greater than 1, and that happens when the absolute value of x is greater than 1. All right, now what does that mean? Well, it means that x can be anything less than 1 or greater than 1. Okay, so that's when the denominator is positive, which means that that's when the second derivative will be positive. So f double prime of x is greater than 0 when we have, x in the interval from negative infinity to negative 1, and from 1 to infinity. Okay, so now we have to figure out when is this going to be negative. So when is x squared minus 1 cubed less than 0? Okay, we can go through the exact same process. We'll get to x squared has to be less than 1, which means that the absolute value of x is going to be less than 1. So that's telling us that it's got to be between negative 1 and 1. Okay, so that means our second derivative, we're at less than now. Second derivative is going to be less than 0 when x is between negative 1 and 1. Okay, so that's telling us our concavity. So I'm going to go back now, put that information down with the rest. So we have second derivative is greater than 0 when x was between negative infinity and negative 1, and 1 to infinity. So this is where we know that it's going to be concave up. Just rewrite the rest of this. It's going to be less than 0 when x is between negative 1 and 1. And that's where it's going to be concave down. Okay, tons of information. So now we have to go back up. We're at the last step, sketch the curve. Okay, so I've already got my point on there. I've already got my asymptotes. The next thing that I'm going to use here is actually coming from where I found those vertical asymptotes. Okay, I do know that when I'm coming in from the left and the right, which infinity I'm approaching. So for example, for positive 1, if I go and take a look back over there, I know that I'm approaching from the right, I'm going towards infinity. From the left, I'm going towards negative infinity. So let me go get that on the graph. From the right, I'm approaching positive infinity. From the left, I'm approaching negative infinity. Okay, when I approach negative 1, as I'm coming in from the left, I approach positive infinity. As I'm coming in from the right, I approach negative infinity. Okay, and so far this is working out with my symmetry because I'm seeing that symmetry about the y-axis. My horizontal asymptotes, I know that I'm approaching 2. Okay, so I'm approaching that horizontal asymptote, and I know it's going to be in the same location as the other part of my graph. All right, so last I'm going to take a look at some of my increasing and decreasing intervals and concavity, so you guys can take a look on your sheets. I know that I am going to have my local max at 0, 0. Okay, so I see my origin point there, and that between negative 1 and 1, it's concave down, and the graph is increasing from negative 1 to 0, decreasing from 0 to 1. So that's down here. I'm going to create that curve just like that, symmetrical to the y-axis. Okay, now I just need to look at those last two pieces. So over to the left of x equals negative 1, I know that I'm going to have a function that is concave up, and I know that it's always increasing. So I'm just going to connect these two together here to create that curve. And then the same thing happens on the right. Again, the symmetry is telling me that, but also I know that it's concave up from 1 to infinity, and it's always decreasing on that interval. So I create a mirror image. Okay, so we have our sketch. We're done with this example. Go ahead and give the other ones a try. Use your guidelines to come up with the information you need to draw it on the graph. See you in class.